loud. Great. Okay, so today I'm super pumped up. We're going to talk about BST. So let's get the whiteboard out. It's going to be a little bit whiteboard led. So BST, we all know the letter B. We all know BS, right? But today we're going to learn about BST. Does anybody know what this stands for off the bat?
Binary search tree.
Hell yeah. Thank you, Henry. Right? Binary search tree. So we've learned about binary trees already, right? So we've learned about trees, specifically binary trees. And we've also learned about binary search, but binary search we were only doing with arrays, right? So a binary search tree is a binary tree just with a couple additional constraints. Okay, and we're going to go over those now. Okay, so for a BST, it has to be a binary tree. So binary tree, right? But the constraints are all nodes on the left subtree. So all left subtree nodes, all left subtree nodes are less than root. Sorry about that horn. I live right by a BQE. And on that note, right, we also have the opposite of that. So we have all right subtree nodes are more than the root. Okay? So our final rule is all subtrees are binary trees. Search trees. That's important. So our binary search tree, it's a binary tree. All left subtree nodes are less than the root. All right subtree nodes are more than the root. You could also say more than equal, right? So a lot of the times BST trees are unique, and that's something you should ask about if you're given a binary search tree question. Find out, hey, will all my nodes be unique, or will some of them have duplicate values? And be aware of how your person wants you to handle that, right? So maybe they want anything with equal to go on the left, or maybe they want anything with equal value to go on the right. And that's just kind of dependent on your specific implementation. But for now, we'll say all left subtree nodes less than root, all right subtree nodes more than root, and all subtrees are also binary search trees. Okay, so let's go ahead and make a binary search tree. Okay, so let's say I start with a 10. I have a 5. I have a 16. Right? I have a 1. I have a 7. And maybe that's it for now. Okay. This is a binary search tree, right? Because if we look at 10, all nodes to 10's right are greater than 10. If we look at all nodes to the left of 10, right, over here, this pen's starting to go, they are all less than 10. And then if we go carry on this pattern, we look at our 5, right? All nodes to the right of 5 are going to be greater than 5. And all nodes to the left of 5 are going to be less than 5. Okay, so let's draw on a couple different possible trees and decide whether or not these are binary search trees. I'm just going to try to find a new pen. All right. Okay. Okay. All right. In the nonverbal feedback feature, please vote. Is this a binary search tree? Okay, got 7 votes. We got half the people voting. Oh, it's the nonverbal feedback feature, Sam. Thank you for that. So if you click on Manage Participants, you'll be able to see yes and no voting. Okay, so we got a couple yeses and we got a couple and mostly no's. Let's talk about it. One of the no's. Do you want to tell us why you say no?
My reasoning was because it only has one. No.
Yeah, that's what I thought. It was just a single number, so it's just a root. It's not a tree.
Okay. All right, because it's just one node. Okay. Someone who says yes, I think we have a few yeses. Can you defend why you say yes?
I thought it can be the roots, and it could be the end of the roots too.
Okay. So let's talk about the rules, right? So what's the main rule of just a binary tree? Anybody remember? Ah, okay. Maybe I should have refreshed that. So binary tree, right? Every node has at most 2 children. Sorry. Right, so a binary tree is every node has at most 2 children. So, is this a binary tree? Yes, right? Because it's a node and it does not have more than 2 children. So we know this is a binary tree. Are all nodes to the left of this less than R7? Yeah, there aren't any nodes. Are all nodes to the right of this greater than 7? Well, there's not really any nodes. So this is, in fact, a binary search tree. This is the smallest binary search tree we can make, just a single node. Okay, so let's try another one. Let's say okay. In your nonverbal feedback feature, is this a binary search tree? Yes or no? Okay. Danny, you're holding on to no? Oh, you switched. All right. So everybody says yes. Okay, I agree, right? Because if we parse this, right, down this 5, and we looked and we went, okay, is everything over here less than 5? Yep. Is everything over here greater than or equal to, we'll say 5. Yeah. Okay, so what about its subtrees? So if we split 8, is everything less than 8? Well, yep. Everything over here is nothing. So this is a binary search tree, right? Same with this, has no children at the end. So this is a binary search tree. We'll look at our left side here of the original. We'll split everything on the left. Yep. Everything on the right. Greater than. Yep. We'll look at this. This is a binary search tree. This is a binary search tree. Therefore, this whole tree must be a binary search tree. Okay, great. So let's do one more. Okay. 5, 6, 7, 8. All right. In the non-verbal feedback feature, is this a binary search tree? Yes or no? Kong's flipping back and forth like wild. Can't decide yet, eh? Okay, so people are mostly settling in on yes, but for the people that are like having some doubt, like Kong and Sam, what is it that you're doubting? What part of this are you not is making you wonder? So Kong says left to left to left, and Sam says because it's a unary tree. Yeah, right. It's a linked list. Very cool. Good identifying, right? So I agree with both of you, right? It's not a great tree because it's really just a linked list. That said, it technically follows all the rules of a binary search tree, right? Every single node to the right of this is greater than the one before. There's nothing less on the left. So technically, this is a binary search tree. And the reason it feels bad is because it's so unbalanced. So why are binary search trees special, right? I guess I haven't actually mentioned this yet. Well, a binary search tree is good because it's sorted data, right? So let's go back to our example where we had 10, 5, 16, 1, 7, and 7, right? When we add this example, we can, if you remember our in-order traversals, right? This would print in order. We'd go all the way down to the left. We'd look at the node, go to the right, look at the node, and then go to the right. So if we were to print this in order, we would have 1, 5, 7, 10, 16. So we're actually able to sort information, just like a sorted array, right? And so when we have a sorted array, it allows us to do pretty cool things like binary search, right? Binary search, if you remember, is log n, which means we're cutting things in half, or the amount of looks we have to do by half with every iteration. So this is great because we could, if we want to look for 7, let's say we had this target of 7, we could go to it. So we're going to say we're looking for 7. We start with our 10, and we say, okay, well, 10 is not 7, but 7 is less than 10. So we don't have to even look to the right at all. We can go immediately to the left. And we can go, okay, 5 is greater than 7. So we'll go to the right. And then we go, okay, well, 7 is 7. And then we can find our 7. But we don't even have to explore anything over here or anything over here, right? So this is saving us time. That's why we're doing log time. And this actually expands pretty nicely. If we had 1,000 elements and our binary search tree was balanced, we'd only have to look at about 10 elements, just like if we were in an array, right? 1,000 to 500 to 250 to 125 to 67 to 33. I can't really do math that well, right? But like 16, 8, 4, 2, and then 1, I think. So something close to those numbers, right? And so that's pretty powerful. So some of you might go, well, why might this be better than just using an array?
Speed.
Well, we could do, but the search for the array is just as fast if it's sorted, right? Because a sorted array, we can do the same thing. Look at the middle and then keep going from the middle to that edge and keep narrowing down our search. But there is a speed aspect, right? And the speed aspect is when we're inserting. Because if I wanted to insert, so if I had the same array here and I had 1, 5, 7, 10, 16, and I wanted to insert, let's say, a 1 or a 0, right? I would have to find here. I wouldn't assume it. I'd have to look in the middle. And eventually I'd end up here. And then I'd have to push it into here. But all of these would have to get re-indexed. And because of that, that's an n operation. That's O of n. Right? Inserting something into an array and keeping it in order is considered O of n. But if I had to do that in a binary search tree, I would go, okay, my 0, less than 10, less than 5, less than 1 goes here. And I don't, and that insertion there is immediate after I found the spot. So instead of it being an n operation, it's a log n operation. So binary search trees start to be really nice when we're inserting and deleting and all that. Okay. Now the catch thing here that maybe you're thinking about is we just saw that essentially linked list. And you're right. So in the worst case scenario, insertion would be n as well for a binary search tree, because we'd have to go all the way through if our entire binary search tree wasn't balanced. So ideally, we want our binary search trees to be balanced. And so a balanced definition is essentially a binary search tree where the children height differ by no more than 1. Okay, so if I had, this is still a binary search tree, right? And this is balanced as well, right? So this is a balanced tree. What about this? Is this balanced? Go ahead and vote if this is a balanced tree. Okay, I'm seeing 11 yeses. Yeah, right? This is balanced because the height for this one, we have a 2, we could say, right? And a 1 here. So that's a difference of 1. And we also have to check the sub trees for everything else. So this is a difference of 0, difference of 0, difference of 0, difference of 0. So just the 1. Okay, let's try another tree to see if it's balanced. I'm sorry that it's so light. Okay, is this All right, we got some yeses, we got one no. Okay. Yeah, I would say this is balanced. So if we were to look here, right, we would say this length we could think is 2. This is 2. Okay, right? That's the max depth for each one. We go, okay. So that's balanced. This node is a balance. Put a B there. Let's look at this subnode. This has a height of 1 and 1 or 0, right? So 1 and 0. This has and 0. That's balanced. That's only different by 1. This one is 0 and 0, so that's balanced. This is 1 and 0 because there's nothing there, so that's balanced. And this, I would say 0 and 0, so that's also balanced. All right, let's try one more. How about that? Let me clear those answers. Okay, is this balanced? Does every subtree's max height differ by no more than 1? Okay. So we got an 11 to 1. Let's see, who's the 1? Ashia, you want to say why it's not balanced?
I was thinking because as soon as you added the next node to the child, then it becomes off balance because if you, all right, let me try to, if you have the first child node to the second child node is a length of 2. And then once you bring it to the third node, it's a length of 3. But there's no node on, there's no second node on the parent child of the second children.
You're talking about this one?
The second one, the one after that.
This one.
Yeah. Does that make sense?
Okay. I kind of follow. Let's talk about it. I like it. Okay. So what's the max depth on this side of this for this child, this tree's children? Right? We can say 3, right? Okay. So we'll say 3. And the max depth for its right side?
3.
Okay, we got our 3. Okay, so that's balanced if we just are looking at this node. This node's good, right? But now, let's go ahead and check the next set of nodes. So on this side's left, what's its depth?
2.
Sure, right? We 1, 2, right? And what's its right?
0.
0. Is that difference more than 1?
Yeah.
That's right. So this is an unbalanced tree. And she is totally right. Right? Because if I had a branch here and a branch here, then we'd be balanced. But since we don't have those, we don't have an even or one-off relationship of those children. Okay, so that's going to hurt us. Now, if we were to implement a BST tree, and we're going to implement a binary search tree today. However, we're just going to implement a naive one, meaning it's not going to be self-balancing. If you want to do that, that's just quite a bit more work, and we don't really have the time for that. I don't think that will help you too far at this point. Those are also called also often called AVL trees, which are self-balancing trees. So that way you can confidently say that this binary search tree's lookup time, insertion time, deletion time, that's all going to be log n. The ones we're going to be building could have the worst case of it being n, because it could be a linked list. Okay, so let's go ahead and start this. So I'm going to screen share. Desktop 2. Right, and so this is our classroom notes area. Just a reminder, we've done binary search. That's where we keep cutting it down in half each time. We've done some trees. We had these tree nodes. Let's go ahead and just rip that for our binary search tree, because it's going to be filled with nodes. And then we also had this nice in-order traversal, which I'm also going to take for now. Right, if you'll remember, this just checks if there's no node, it just returns. Otherwise, it's going to look to the left, it's going to log the current node, and then it's going to go to the right. And so it's going to print all those nodes in order. So let's go ahead and write a binary search tree class. So let's call this class BST. And so it's going to have a constructor. And the first thing that the only thing it's going to need, that we're going to need access to, is this root, which will default to null. Okay, so we'll be able to make this tree. So we want to be able to insert in the tree, right? That's important. So let's go ahead and make a insert method. So we're going to say insert. And this is going to take in some value. And we're going to use recursion for this method, so we can keep using this specific node, and we'll check if its value exists. So let's go ahead and call this root, or I'll call it node. Sorry. And let's just default this to this.root. Okay, so if we were to start with nothing, right? If we just had the number 5 or 10, I said, hey, I want you just to start with 10. What's the first thing we would think about doing? What would we want to check? How do we add that to this tree?
Maybe if there's a root.
Yeah, sounds great, right? We want to check if there's a root. And because if there's not a root, we just want to go ahead and make it. That sounds simple enough. So let's go ahead and do that. So we'll say, hey, if this.root, or specifically if there's no root. Oh, I'm seeing there's something in the chat. Let me just. Also, should we check if the numbers are sorted? So we don't have any numbers right now. So that's a great question, Henry, right? What we're trying to do is we're building this tree from scratch. So as we insert into this tree, we're going to have to make sure that they keep true to their sorted pattern. So in this case, we'll say, if there's no root, let's go ahead and just make the root. And we'll say, oops. This.root is equal to new tree node, and we'll pass in our value. Okay. That sounds good enough. And we should also stop. I don't want to keep returning. I could write everything, but to me, this feels a little bit cleaner. Okay, so if the tree node if the tree is currently empty, right? If tree is currently empty, set value to be the root. Great. Okay, so now we have this tree node of 10. And let's say the next number we put in is 5. So we're checked. Okay, we do have a root. It's 10. So what do we want to check for next?
You want to check the values of the root and the value that you're looking to add and see if it's greater or smaller than the root.
Awesome. Okay, so if, I like that. So we'll say, hey, if our value is less than our node dot value, or node being root here. Maybe I'll just call this root to stay consistent. Okay. And this root is still just referring to like the main root. Okay, so we say, okay, if it's less than our root value, we're going to want to do something. Else, we'll want to do something else, right? So in the event that it's less than, so in this case, we have a 5. So we want to insert a 5, and we see that it's less than. What do we want to do next?
You said that is.
Sorry, Henry?
You said that if the next number is 5, what's going to happen?
We want to insert a 5 into here.
I'm sorry, repeat that again?
We want to insert a 5 into here. We know that it's now less than 10. So what else might we want to do? What would be our next step?
Push it to the left, no? If it's 5?
Well, what if I had a node?
Maybe, yeah, I was going to say maybe see if the 10 has children to compare that 5 to, because what if they have a children that's like an 8 and you got to search that node again?
Exactly, right? So we got to check first. So if our value is less than our root, we know we want to go to the left, but we don't know if we already have a child here. So we have to just do a quick check. If there's no root dot left, so in the event that there is no children, we'll do what Henry's saying, which is essentially just put it to the left, right? Where we would say root dot left is equal to new tree node of value, right? But Ashia says, what if there already was a left? So if there's already a left, right, this is where we get to use our recursion. And we can say, well, this dot insert, and we'll pass our value, and then our new root this time will be our root dot left. So let's think about that.
Question, where are you calling where's the insert coming from?
It's going to be part of our class.
Oh, line 14, Henry.
Thank you, Ashia.
Oh, gotcha. Yeah, thank you, Ashia. Right, so we're writing insert right now, and it's recursive, so it's going to call itself. Right, so we're looking here. So we go, first we're checking, okay, so we're going to the left, because we've determined our value is less than our root value. But now we're saying, well, is there a child? And if there's not, we'll do what Henry said, which is just assign that in there. But if there already was a child, so now if we were adding a 3, and we were here, and we go, okay, we'll go to the left, and we go, well, there is something here. So then we're going to call insert again and make this the root of that call. So the first thing that would happen is it's going to check for a root in the whole tree, and it sees, well, that's already there. Then it would check if our root, which is our 5 here, our value, is this greater than our current value? And we go, well, it is. So then it checks to see if it has a left child, which it doesn't. And then it would insert that 3. So to write some notes, right? So if our root is less than our value, we have to first check if it has no left child. If it doesn't, it becomes the left child, right? Otherwise, call insert again on subtree, right? So in the event that it's right or equal to, right, we can do the same thing. So now we just check, hey, if our root dot right, so if we don't have a thing on right, then we'll just make that root dot right is equal to our new tree node, and we'll pass in our value. Else, we have to call our insert with our value and our root dot right. And that's it. That's our insert. So let's go ahead and try this. So let's make some stuff. So down here, we'll say, let's do let tree1 equal new BST. Right, so this is our new binary search tree. Let's go ahead and insert some stuff. So let's start with inserting 10, and we'll just do a few things. So we'll say 5, 16, 1, 7, oops. And we'll go 16 again anyway. Right, and so then let's go ahead and see if we can print this. Let's say console.log tree1. See what this looks like. Node binary search tree. And we see that we've got this value of 10. We've got this left of 5, this right of 16. We can't see further than that, but we can also try our in-order traversal. So let's go ahead and do our DFS on our tree 1. We'll go ahead and run this. Oops. Something should have happened, eh? Interesting. Is it calling this? DFS in order. Console log our node.value. Is it like not hitting this? Just quick check. It's hitting it. For some reason, oh, we're saying val. Oops. Oh, it is val. Interesting. Anybody have any ideas what's going on here? Tree 1. Interesting bug here. Maybe there's something wrong with our in-order traversal.
Corey, maybe if you put lines 46 through 52 on top of the DSFs, the DFS, would that make a difference?
Which lines are you worried about?
Where you creating the tree? Like if
Right
you,
here?
Yeah, if you move all that on top of the function, would that work? I don't know.
I don't think that would make a difference, but happy to try it. A little confused why it's not working. So, well, let's console log our node, shall we? Let's see why this isn't working. So our node is coming in. Node. Are we spelling left? Must be doing something silly. Ugh. Okay, if there's no left, we'll just add it in. Interesting bug we have here. I'm so confused right now. Huh.
Try
Let's
changing.
see. Node. Dot left. Dot val. And dot right. It's a little live action programming here.
Maybe it has to be root instead of node.
What? No, that really shouldn't matter because these are just variables. This should be able to say anything.
Why, Corey? Why whenever you call the function, why does it have a line under it? Maybe the DFS in order. Maybe if you change the name, try changing the name.
Sure.
There's a line under it. I don't know.
Sure. I'll just call it DFS. I can't imagine why that would matter. But this is weird. This is so weird. I love it, but I didn't want to spend any time on this really.
You spell BST and BTS.
Wait, where are we at?
Oh no, it's spelled the same. Sorry. Forget it.
Oh damn! I thought you had something there.
I thought so too.
So it's turning out undefined. So our tree node, like this is logging on the very first call, right? And this is the root. And so I think I actually have to do tree node dot root. And I think that's going to solve our problem. That's kind of a stupid mistake on my part. But, you know, it's a tricky thing, right? So, right, the error is that my tree instance looks like this, right? It looks like this object, right? So this is not just a node, which is what it's supposed to be called on. This is the whole instance of my binary search tree. So we need to call it on the root, which is actually a node that has all its left and rights. Okay. Sorry about that. Super annoying. Okay. Right, and so just to prove to you all about some order, right, I'm going to make a second tree here. And this is why our solution is considered naive, is because if I import this, put in the same numbers, right, I'm still going to get the exact, whoops. I'm still going to get the exact same order. We'll see. Even though one is just a linked list, right? So a binary search tree can look different, even though it has the exact same numbers, and it's still in a sorted manner. So that's something to think about.
Hey, Corey.
Yeah.
Should we have like an error case for like the two 16s because it prints twice, but shouldn't it only print once because it's already included in the tree?
Yeah, so I hear you. So Ashia, so this really depends on the like your interviewers, what they want. So in this case scenario, I am allowing duplicates in the binary search tree, and I'm just saying that any duplicate should be part of the right subtree.
Okay, I got it.
But we also could have made it so that it's not in the tree at all. Which in that case, we could have thrown errors and stuff. But for now, I'll just remove both. But it just depends on how the individual wants to handle that. Okay, so let's go ahead and try to write a search now. All right, so let's say we want to search for a given target just to see if this exists, right? Let's say we want the node back of where this exists. And we will also pass in this root again, and we'll have it default to our this.root. And in here, we can start setting up this search. Okay, so we've got a couple notes here. So the code's going to look pretty similar again. So if we're looking, right, first thing, how do we know for sure that the target is not in this tree? What can we know for sure? What would be a base
the
case?
question? I'm sorry.
What would be a good base case? So if we were given a binary search tree, or so we thought, and I said, hey, is this target inside of this? When would we know for sure that it's not?
When there's nothing in there.
Yeah, exactly,
Yeah.
right? When there is no root. If there's no root, we can just go ahead and return false, right? If there's no root, we're not getting it. Now, in the event that if our root.value equals to our target, well, then we can go ahead and return our root, right? Or we could return the value, but we probably already know the value because that's the target. So we probably would want the node back. If we just want to know if it existed or not, we would return true, right? But in this scenario, we'll say we actually want the node. So, okay. And so what are some other checks we might want to do? What else might we look for? So if this is our tree here, right? Right, if I'm looking for 6, and this is our tree, and I'm at right here, which way would I want it to go?
If root that left?
Yeah, so I want to go.
Oh, if root that right, sorry.
Well, 6 is going to be less than 10, right?
Oh, of the second node I meant. So it's going to be on the left side, yeah.
Yeah, so exactly. So for this one, we're going to want to go and check if it's in the left subtree, right? So let's handle that. So we go, okay, so if our or we'll say if our target is less than our root.val, well, then let's go ahead and check out the root subtree. So we'll say this.search, pass in our target, and we'll say root.left. On the left, where's the only place left for us to check?
To the right.
Thank you, right? Else we're going to the right. So we can just go ahead and search our target and go root.right. Bada bing, bada boom, right? And this should be everything that we want. So let's go ahead and try it. I'm just gonna get rid of BST2 for now. I'll just leave it, but we're gonna look for our 1. And so let's go ahead and say console.log. And we'll say tree1 dot search. And let's take a look for our 7. Right, so we should get back this node here. Okay, let's go ahead and see if we get it.
Tree.root?
Yeah, no. Because we have the root. It's checking right. It defaults to this root here. Let me just check. So I'm just gonna move this up so I can see it better. Okay, so we've got our insert. So we've got our 7. We are passing in our dot search. This should, so many bugs while coding, right? Totally normal, unfortunately. This should be giving us back our root, our actual value, but it's not. So let's think about why that would be the case. So let's go ahead and start to debug and say target and root. And we see that our target was 7, our tree node was 10. Then we went to the left and we said our target was 7, our tree node value was 5. Our target was 7, our tree node value was 5, but yet we still then returned undefined. So I think that's interesting. So if we should be saying target, let's just check this line of logic, is equal to root.val. And we should see a true in there. And we do. So for some reason, it's just not like returning that root, even though this statement is in fact true. This is the same wording. It's just in different order, but I'm going to make it the same anyway, just because I know for a fact that this console log works. Okay. Still getting undefined. I think it's, why would that be? That's because we're not returning here or
Don't
here.
you have to put in two arguments for search?
I do not, because this is a default argument that will be the root of our tree.
Okay.
So it's because we didn't return from those other calls. So now we get it. Right? Remember, if you want something to return, it has to. So this call does return when it's equal. But the first time we went left, and we have to return still. Otherwise, eventually it bubbles up, but then nothing actually returns from it. So that's important. Okay. And let's try one with a color, something that we're not in there. So if we say 8, we can see that this is false, right? So the good thing about this is that this is happening in log n time, because it only has to travel as deep as the height of the tree. So if it's balanced, it's log n. If it's an unbalanced tree, worst case scenario, it is n. Okay, and so that's pretty much everything that I really wanted to talk to you all about for binary search trees. They do come up a lot of times in interviews. Well, not like a lot. They can come up in interviews. When someone's talking about binary trees, it's always good to ask if they're talking about a binary tree or binary search tree, and if that binary search tree is balanced, because those all have very different implications, right? If I was searching for something and a binary tree, it's going to be n, because I don't know where it is. It's random. Typically, when you're dealing with a binary tree, it's usually a binary search tree, because there's a benefit to that, to it being a binary search tree, and there's not really much of a hindrance. Like, there's no benefit to having it be a binary tree over a binary search tree. So it's better to have that data in some kind of sorted way, usually. Okay, any questions on that? Any questions at all? Okay, so this leak code problem is a little bit tricky, and we're going to do it in breakout rooms. I'm going to check if search is less than root or more. Okay, so here's the leak code problem that I want us to try. Let's go ahead and give ourselves 20 minutes to try to solve this. I'm going to add some rooms. Oh, we only have 15 people here. That's bizarre. Okay. All right, I'm going to create these breakout rooms. They look pretty random to me. Okay, so let's spend 20 minutes to try to solve this problem, and then we'll talk about it. Okay? Any questions before we go into this? All right, cool. Let's do it. All right, cool. I think that's everybody. We got a small class today. Okay, on a scale of 1 to 5, how did this go? 5 being great, 1 being awful. Okay, so we got 10 out of 13 people, 11, 2 more. What's it gonna be? All right, well, that's long enough. I'll share the results. So this is where we're at. Not great, right? Not ideal, it's a little tricky. I know it says it's an easy problem. I don't totally think that's the case. I think it's kind of tricky. What was tough about it? Let's talk about it. What was tough?
I think for our group, we were having like a hard time figuring out how we were going to actually search through like the depth of the tree and compare the lengths to each other, like to kind of hit that mark of no more than 1. And yeah, we were just struggling really hard on that one.
Okay. Yeah, so having some trouble identifying the depth of the tree. So, okay. Any other things that we got kind of hung up on? No, that was it. Finding the height. Well, okay. Let's think back. I believe one of our questions on our DSA exam was to find the max depth of the tree. Do we remember that question?
Yeah.
Yeah, right? We actually had that question of finding a max depth. So what about if we wanted to find if the max depth of the left side and the max depth of the right side And we wanted to just compare and see if those were more than one off. Well, if we wanted to write something like that, let's go ahead and break this down. So I will share screen. Okay, so we've got this, our lead code problem here, right? And we know that we've written a height before, right? We've done that before. We've written a get height. So let's go ahead and start with that because we know we're going to want to be able to get a height. So if we want to be able to get a height, we'll take in a root. And we know right away that if there is no height, maybe we want to just return 0. So if there is no root, we'll just return 0. Some people might want to return -1. It just kind of depends on what you consider to be height. I'm going to consider this 0. And so if we remember what that one before was, we just want to get the max height. We would just say return 1 because plus whatever the max is from our left and whatever the max is from our right. So
Sorry, I
we'll
have
say,
a question.
yeah, go for it.
Like if there is like a root, we return true or false or 0?
Well, if there's no root, good catch, we want to return 0, right? Because we'll say there's no height. However, if there is a root, we know that there's at least a height of 1, and then we also want that to be plus whatever the max height we can get from either side there. So we'll say get height of our root dot left and our get height of our root dot right. So this should be giving us some kind of height of some node, right? And so in our is balanced, we can go ahead and check because we really care about the height from the left side as well as the height from the right side. Again, if we're past no root, we can go ahead and just return true because no root, we can say, I think this one wants there to be, I'll just leave it for now. Doesn't matter. So let's go ahead and just say return. Let's pretend. And we say return. And we could say, we'll get the height of our root dot left. And we want to subtract it. Let's say get height of our root dot right. And since we don't know which one of these is going to be bigger, what's something we could do?
Absolute.
Yeah, exactly. That's Brandon, right?
Yeah.
We can use math.abs so we can get the absolute difference between the two. And so we can say, hey, why don't we see if this is less than or equal to 1? Okay. And we'll run it. I'm sure we're gonna see some mistakes here. And we run it. And okay, it works for this one, but okay, let's submit it. And we go, okay, what's gonna happen? Doesn't work because we got this empty array. And we don't have a right or a left property on an empty array. So if we're given nothing, it wants some value. It's not telling us what it's expecting, but I believe it expects it to be true. But we can test that. Okay, so let's say if I wanted to think that if there was no root, I could just, let's say I'm guessing false because that feels like the right instinct. But then when I run it as a sample test, I'll see, it expects true. Okay, whatever floats your boat, right? So we just flip it to true. And this time we'll submit again. And we should see a new thing. So we go, okay, we got true this time when it was false. So let's take a deeper look at this test case. Let's visualize the tree. this case, right? We remember this. This was not balanced, right? Even though we kind of thought it might look balanced, because for this node, it's balanced because it has a depth of 3 here and a depth of 3 here, right? But for this node, it's not balanced because it has a depth of 2 and a depth of 0. So our function that we have right now doesn't actually account for any of the other subtree nodes. All it's looking at is the root. So, but in fact, all the subtrees also have to be balanced. So instead of returning here, let's go ahead and set this to a variable called difference. And instead, we'll return to make sure that we have a difference. So return that our difference is in fact true. And, right, we want to check if our left side is balanced and our right side is balanced. So we'll just call is balanced on root.left and is balanced on root.right. Let's go ahead and run that now. So we run the sample. Okay, so this time it did detect that that's false. So let's go ahead and submit it. And we'll try it out and we'll see, okay, we passed all the tests. Any questions on how we got there?
Could you please repeat the explanations?
Like the whole thing?
Or not just from 19 to the bottom?
Yeah, that's the whole thing. Okay. So what we saw, the test case specifically told us that when there's no root, it should return true. So we updated that. We have a difference that we're keeping track to make sure that the difference of each side's height, absolute difference, is less than or equal to 1. So a difference of 0 is fine, a difference of 1 is fine. So we just got the height of the left and the height of the right and found the absolute difference. And so if that was true, and all of the other nodes also were balanced, because our left side also, our left node needs to be balanced as well as our right subtree, only then would we be returning true.
Thank you.
No problem. Any other questions there on the logic of that problem? Right, so this is a little bit tricky, but it's definitely something that's within our wheelhouse. And it's definitely something, if we're having struggle on this one, we just got to keep grinding and doing more LeetCode problems on our free time as well. I do have one more problem that I wanted us to try today. I'm just going to pull it up now. Okay. Stop share. I'm throwing it in the chat. And so for this problem, you'll want to convert a sorted array into a binary search tree. Okay, so go ahead and give this a shot. Let's give it another, I guess, 20 minutes, and then we'll go over it, and then our day together will be done. Okay? Any questions before we head out? I'm recording. Okay, hopefully you can see the results right now. So again, not great, but not horrible. So, you know, whatever, it's where we're at. It is only 20 minutes to do a problem, so, you know, that's not easy. So let's talk about it. What were some of the things we found tricky about this? What were some of the observations, maybe things we noticed about it? What do we find? Rusty, okay, yeah, sure. Thanks, Henry. What else? Did we notice any kind of pattern with this? Right, so we had
There might be some sort of helper functions, or
okay.
maybe that you might have to like set variables and perhaps use a while loop. There are so many things we discussed.
That's cool. I like that. I like a lot. We got lots of ideas. No shortage of ideas. I love that. So we were given some pieces of information, right? And that special piece of information was that we had a sorted array, right? So the data was already sorted for us, already, right? So if we had a sorted array, let's say we had 1, 2, 3, 4, 5, 6, and 7. What's something we might, like what would be our root node?
4.
4.
Or
How did you figure that?
because it's the middle number, since it's already sorted, so you know which numbers is going to go to the left and which numbers will go to the right.
Okay, yeah, I like that, right? So we're totally right. 4 should probably be the middle. And this is great and that's because we want it to be hopefully as balanced of a tree as possible as we can, right? Because technically we could just make a linked list that said 1, 2, 3, 4, 5, 6, 7. But that's not really a great binary search tree. Ideally, we have it as balanced as possible. So we know that if we were to split it in the middle here, we could have 4 as a root. And so if we had 4 as a root, now we can look at this side and this side. So if we were looking at the left side here, what would be a good left child to our 4?
3.
3 would be a good left?
No, 2.
2, right? Because 2 would work quite nicely for that. Right? And then we could call it here on this side, and we'd have our 1, and we call it here, and we have our 3. And over here, we have what would be a nice right side node here?
6.
6, right? Because then we would have this nice 5 when we called with this side, and we would have this nice 7 when we called with this side. So what's a pattern that's emerging?
Getting the mids of the new splits.
That's
Taking it in
what's
half.
that notation? What's that notation called? Log n,
Well,
right?
well, we're cutting the problem in half, but we are still going to have to touch every node. So this is still going to take n time. But yeah, I heard some talk about the pattern here is we're taking the middle node and we're making that the root node. Okay, so let's think about that in code a little bit, shall we? So let's go ahead and share my screen. Oh, I hear the motorcycles. Okay, so if this was our function, this sometimes annoys me. It doesn't always, but it's annoying me right now. So I'm just gonna make it ES6. Okay. Okay, so we've got our nums. Now, when would we be done? When do we know that there's nothing left to do?
When nums equals 0. Oh, nums.length equals 0.
Sure, yeah. So if nums.length, because nums is an array, if that were to equal 0, we could just go ahead and return null, right? Because there's nothing there. Okay, I like that. So then let's go ahead and find our root. So let's go ahead and say root, or let's find our mid first, we might as well. So we'll say const mid index is equal to math.floor, right, of our nums.length divided by 2. Okay, so now we've got this nice middle, and let's go ahead and give our root that value. So let's go ahead and make a root. So we'll say const root, and so nums at our mid index is going to give us back some value, right? some number. So in this case, it would give us back like a 0. But we actually want it to be a tree node because this is going to be a tree. So let's go ahead and call our new tree node. Pass that in as our value. Right? And so now we've assigned this, so we can look and we could say, well, the left side is going to go to the left, and they can figure themselves out. And the right side is going to go to the right, and they can figure themselves out. So if I think like that, I could say root.left is equal to, and I could call our function again, sorted array to BST, and I could just slice from the left. So I could say nums.slice. It could go from 0 to our mid index. Keep in mind this is exclusive because we don't want to include our mid index because our mid index is currently already valued at our root. In the same light, we can also do our right side. So we'll say root.right is equal to our sorted array to BST, and we would slice. And where would we slice for this one?
The next value over.
Yeah, the next side over. So what would I have to type in inside of here?
Mid index +1.
Excellent, right? So we have to do that +1 just because the starting value in our slice is inclusive, but we want to exclude our mid index. Excellent. And then at the very end, we can just go ahead and return our root. And so we can run. Check to see if this works, what kind of bugs. Looks like that answer is accepted. Let's go ahead and submit. And we see that this also works. Any questions on this one? Looks like I have a notification. Okay. Yeah. So the idea is we are essentially just keep cutting it down. So we're taking the middle and we're going, okay, that's going to be our root. And then we're going to root.left is what is going to evaluate to whatever comes out of this call again. Same with the right's going to be whatever comes out of this call. So this call will take the root and it will look at 2 divided by 2 is 1. So we'll look at the index 1 and that's going to become the root, which is, we'll see here. And then we'll say, okay, and that's left side is going to be whatever comes out of here, which is going to have to be -10. And it's right side. There won't be a right side because there's nothing left in that array. And this mirrored version of that is going to happen on our right side. Right, so if you're worried about the time complexity of this at all, right, because we are doing a lot of slicing, so that could be considered potentially annoying. If we didn't want to slice, we could keep track of a left and a right, right? Let's say we wanted to do that. Wait, any questions on this solution here first before I continue?
I have a question. How is it? It just looks so similar to a log-n to me. So, like, what's the difference?
Well, the difference is we're still touching every single node. So log n would be if we were looking at the left side and never looked at the right side.
Oh, okay. I get it. I get it now. I get it. Thank you.
Yeah, so no problem. So we're still having to check every single node. So, and that's going to be unavoidable, right? Because how can we transfer everything over without touching everything? We can't. So this, I believe the solution should be running in N. But there are places where we could do minor improvements to get this a little faster. So we could, in addition with our nums, we could add a left, set that to 0, and we could add a right, set that to our nums dot length -1, right? So now, just like a traditional kind of binary search thing, we can find this new middle. And so for this one, it wouldn't be if nums is our length, but instead if left is greater than our right, we would return null. Our mid index would no longer be by num's length, but it would be if left plus right divided by 2. Our root would remain the same, but our left would be no longer have a slice. It would just be that we want our left and our mid index, what is it, -1? And this would be our nums with our mid index +1 and our right. So this would also be doing the same type of movement. Let's just double check to make sure we didn't miswrite something. Looks like we did make some mistake because our output's different. So let's see, what would be this? What would be wrong with this? Okay. So if we wanted to go to the left, we would want to go to our mid index -1, right? Okay, and our right would be our sorted array nums mid index +1, comma right. I wonder why that's wrong. Is that an issue? Interesting. So we're it's definitely not, this is not working in the way that I was hoping that it would work. But I'm fairly certain I actually.
Nums left -1. What would you took that off? Don't do that.
No, I'm still trying to figure this out. If nums is less than, maybe, or equal to. Nope. All right. So I have written this solution in the past. I'm gonna just compare it and see. I want to maybe this old solution didn't work. Also possible. Oh, maybe it never worked. Oh. Oh, maybe I put in the wrong answer a year ago. Okay. So I still feel like this should work. Anybody else feel like that it should work?
I don't think so
Yeah.
because oh,
Okay.
Well, why?
because you didn't put like a case for. I feel like that you're missing a. I don't know what it is, but I just feel like you're missing a case. Like in the if statement, there's a case missing. That's all. I don't know.
Yeah, maybe. Interesting. Why does this not work? So let's go ahead and look at what our root is each time. Dot log. Let's see what our left and our right are. Okay, so our left is 0, right? So what's our mid? If we can't figure this out, I'll work on this more later. I don't want to take up really too much of your time. Well, mid index. Because I may not have gotten it to work a year ago. I might have quit. Just not remembered. So we do touch every element. Oh, you know what it is? We can, no.
Yeah, that's what it is. Your left, you're setting it for 0, and your right, you're setting it for 0, and there's numbers smaller than 0. Oh wait, the left, you're setting it at 0. So maybe it's not reading the negative numbers.
No, the left is part of the index.
But
These
you're
are all-
initializing it in 0 though on line
Right.
9.
It's the very left index.
Oh, okay.
Right? 'Cause
Oh,
it
sorry.
in the
Okay.
middle.
Got it. Yeah.
No, that's fine. I appreciate the help, right? I mean, there's obviously a bug in here, just not sure what it is yet. The left, let's stay the same. I really don't know why this isn't working, but so I'm just gonna copy it and I will work on it later, and I'll let everybody know if I figure it out why that didn't work, and we'll just stay with our initial answer of using slice, which looks like this. Good. Okay. So I'm gonna look into that because that's kind of bizarre. Feels like it should work. Any questions on this one though? Just taking the left side and then taking the right side. Okay. That other one's gonna eat me alive. I'm gonna find that out.
Same,
No.
man. I'm already annoyed too.
Yeah, I don't know. If anybody does figure that one out, let me know as well. All right. Well, that's everything that I have planned for the day. Definitely, do keep working on that CTA, right? Please finish that.